What if I told you that 97% of people learning machine learning are doing it completely wrong? They're memorizing Python syntax like it's a prayer. They're collecting Coursera certificates like Pokemon cards. They're copying Stack Overflow code and crossing their fingers. But here's the uncomfortable truth that nobody wants to admit. Machine learning isn't about being a code monkey. It's about becoming a pattern whisperer. Think about it. Every time Netflix knows exactly what trashy reality show you'll binge next. Every time your phone autocorrects duck to something more colorful. Every time a Tesla swerves to avoid that squirrel. That's not math. That's machines learning to see the invisible threads that connect our chaotic world. And once you learn to see these patterns too, you'll never look at data the same way again. But here's where it gets spicy. The most powerful data scientists in the world, they're not the ones with the most GPUs or the fanciest algorithms. They're the ones who ask better questions, who know when to trust their model and when to call BS, who understand that behind every prediction is a story, and behind every story is a human need waiting to be solved. In the next 45 minutes, you're not getting another dry tutorial that makes you want to slam your laptop shut. You're getting the mental models that separate the AI builders from the AI wannabes. By the end, you won't just understand machine learning, you'll see it everywhere, in every targeted ad that creeps you out, in every spam email that somehow escaped Gmail, in every job application that mysteriously got lost in the ATS system. Ready to see how deep the rabbit hole goes? Let's crack open hands-on machine learning and steal the secrets that Silicon Valley charges $200K salaries for. Section 1. What is machine learning really about? All right, before we dive into the code that'll make your computer think it's smarter than you, spoiler, it's not, let's get brutally honest about what machine learning actually is. Because if you think it's about machines becoming sentient and plotting world domination, well, you've been watching too much Netflix, which ironically uses machine learning to keep you watching too much Netflix. Meta, right? Here's the thing, machine learning is just pattern recognition on steroids. That's it. That's the tweet. When Arthur Samuel coined the term in 1959, he basically said, what if we stop telling computers exactly what to do and just let them figure it out? Crazy idea at the time. Now, it's why your phone can recognize your face even with that questionable quarantine beard. Think of it like teaching a toddler the difference between cats and dogs. You don't sit them down with a PowerPoint presentation defining fur texture coefficients and ear angle parameters. You just show them pictures. Cat, dog, cat, dog. Eventually, their little brain goes, aha, pointy ears and gives zero dams. Ich like a cat. Floppy ears and desperately wants approval. Ich like a dog. That's literally what we're doing with machines. Except instead of a toddler, it's a bunch of matrix multiplications. And instead of awe, the response is usually, why isn't this working? But here's what Aurélien Géron gets that most textbooks don't. Machine learning isn't about the algorithms. I know, shocking. It's about the loop, the beautiful, iterative, sometimes frustrating loop of data, learning, feedback, improvement. You feed it examples, it makes guesses. You tell it how wrong it was, usually very. It adjusts, rinse, repeat, until suddenly it's diagnosing diseases better than doctors who spent 12 years in school. No offense, doctors. Now, you're probably thinking, okay, but how does the magic happen? Well, buckle up, Buttercup, because here's where most people get lost in the sauce. Section 2, your first AI project, a real-world walkthrough. Let me tell you about the moment everything clicks. It's not when you finally understand backpropagation, nobody really does. It's when you build your first real ML project and watch it actually work, even if it's held together with digital duct tape and prayers. Géron knows this, which is why he throws you into the deep end with a California housing price predictor. Because nothing says practical application like the impossible dream of homeownership, am I right? So picture this. You've got a CSV file that looks like someone sneezed numbers all over a spreadsheet. Longitude, latitude, median income, ocean proximity, it's chaos. Your first instinct, panic. Your second instinct, Stack Overflow. But wait, before you copy-paste your way to confusion, Géron drops some wisdom. Understand your problem first. You're not just predicting numbers, you're modeling human desires, economic forces, the eternal California question of, but how far from the beach? This isn't data science. This is digital archaeology, and you're Indiana Jones with a Jupyter notebook. Here's where it gets addictive. You load that messy data into pandas, and suddenly you're not looking at numbers. You're seeing stories. That weird cluster of cheap houses, probably near a freeway. That one insanely expensive outlier. Some tech bros disruption mansion, no doubt. You plot histograms, scatter plots, correlation matrices. Each visualization is like turning on a new light in a dark room. Oh, that's why prices spike there. But then comes the plot twist nobody warns you about: the train test split. Sounds simple, right? Just randomly chop your data. Wrong. That's like practicing for a marathon by only running downhill. Géron shows you stratified sampling, making sure your split represents the real world. Because if your training data is all beach houses and your test data is all desert shacks, congratulations. You've built a model that's as useful as a chocolate teapot. And this is just the appetizer. Wait until you see what happens when we let machines draw boundaries. Section 3. How machines learn to classify you. Pop quiz. How many times today has a machine classified you? If you said less than 100, you're adorably naive. From the moment your phone's Face ID decided, yeah, that's still you, despite the bedhead, to every email Gmail sorted, to that moment LinkedIn decided you're likely to be interested in cryptocurrency jobs. Thanks, I hate it. You've been classified, categorized, and computationally judged. But here's the kicker. Classification isn't some big brother conspiracy. It's just machines learning to play the world's most elaborate game of spot the difference. And Géron's about to show you exactly how they do it. Enter MNIST, the hello world of computer vision. It's 70,000 handwritten digits, each one a 28x28 pixel grayscale image. Tiny, grainy. Looks like something from a 1980s calculator, but to a machine learning model, it's the Rosetta Stone of pattern recognition. You flatten each image into a 784 number vector. Because machines don't see pictures, they see lists of numbers. How sad is that? You feed it to something called stochastic gradient descent, which sounds like a prog rock band but is actually just a way of saying guess, check, adjust, repeat. And then something magical happens. The model starts getting them right. Not all of them, but enough to make you go, wait, how did it know that chicken scratch was a 7? But Géron doesn't let you celebrate yet. Oh no, because accuracy, that's for amateurs. He introduces you to the confusion matrix, basically a report card that shows exactly how your model is screwing up. Mistaking 8s for 3s, your model needs glasses. Confusing 1s for 7s. Time to work on those diagonal strokes. It's like being a teacher, but for artificial neurons. And just when you think you've got it figured out, he drops the precision recall bomb. See, if you're detecting cancer, missing a positive case, false negative, could kill someone. But if you're filtering spam, marking legitimate email as spam, false positive, just annoys people. Same math, wildly different stakes. Suddenly, you realize classification isn't just about being right. It's about being wrong in the right way. Mind blown, yet. Just wait until we talk about how these models actually learn. Section 4. Gradient descent, the GPS of machine learning. Okay, story time. You're at a party, remember those? Someone blindfolds you, spins you around, and tells you to find the beer pong table using only your sense of balance. Every step you feel, if you're going uphill or downhill. You stumble towards downhill because that's where the table probably is. That's gradient descent. Except instead of finding beer pong, you're finding the optimal parameters for your model. Way less fun, but way more profitable. This is where Géron separates the "I copied this from GitHub" crowd from the "I actually understand what's happening" elite. Because gradient descent isn't just an algorithm, it's a philosophy. It says I don't need to see the whole mountain. I just need to know which way is down, and I'll get to the valley eventually. Your model starts with random guesses for its parameters. Terrible guesses. Like wearing socks with sandals level bad. It makes predictions, measures how wrong it is, the loss function, and then, here's the magic, calculates which direction to adjust each parameter to be slightly less wrong. Not perfect, just less wrong. It's basically machine learning's version of progress, not perfection. The learning rate is your step size. Too big? You're that person who takes the stairs 3 at a time and face plants. Too small? You're shuffling forward like a zombie, and training will take until the heat death of the universe. Finding the sweet spot, that's an art form. But wait, there's a plot twist. Sometimes you get stuck in a local minimum, a little dip that feels like the bottom but isn't. It's like finding a mediocre taco truck and thinking this must be the best food in town when there's actually a Michelin star restaurant around the corner. That's why we have momentum-based optimizers like Atom. They remember where they've been and use that history to power through the fake valleys. Smart, right? The beauty is, this same principle works whether you're training a simple linear regression or a neural network with millions of parameters. It scales, it adapts, it's elegantly universal. And once you truly grok gradient descent, you'll never see optimization the same way again. Speaking of seeing things differently, let's talk about SVMs, the Swiss Army knife of machine learning. Section 5, Support Vector Machines, Slicing Through Data. Picture this. You're at a wedding. Machine learning is everywhere, even at weddings. The dance floor is split, bride's side doing the electric slide, groom's side attempting to floss. Your job? Draw an imaginary line that separates these two tribes with maximum drama, margin. That's essentially what support vector machines do, except with data points instead of drunk relatives. SVMs are the perfectionists of the ML world. While other algorithms are like, close enough, SVMs are obsessing over finding the best boundary. Not just any line that separates your data, the line with the biggest cushion on both sides. It's like social distancing for data points. The points closest to this boundary? Those are your support vectors, the drama queens that define everything. Move one, and the whole boundary shifts. They're like those friends whose mood determines the entire vibe of the group chat. The other points, they could disappear, and the model wouldn't even notice. Brutal, but efficient. But real life is messy, shocking, I know. Sometimes your data is like a Jackson Pollock painting, red and blue splattered everywhere with no clean separation. That's where Géron introduces the soft margin, which is ML speak for, let's be realistic here. You allow some misclassifications because forcing perfection would create a boundary more twisted than a Christopher Nolan plot. And then, plot twist, the kernel trick enters the chat. What if your data is arranged in spirals, moons, some weird donut shape? SVMs go hold my beer and project your data into a higher dimension, where those complex patterns become linearly separable. It's like solving a maze by flying over it. Cheating? Maybe. Genius? Definitely. But here's the thing about SVMs. They're amazing for smaller datasets, but start sweating when you throw millions of examples at them. They're like that friend who's great at intimate dinners, but freezes up at big parties. Which leads us perfectly to our next topic. What happens when one model isn't enough? Section 6, Decision Trees, if then magic. Remember playing 20 questions as a kid? Is it alive? Does it have fur? Does it bark? That's literally how decision trees work, except they're playing 20 questions with your data. And instead of guessing dog, they're predicting whether you'll default on alone. Decision trees are the most human-like ML algorithm. They think in if-then statements, just like your brain, when deciding whether to text your ex. If it's past 2 a.m., then no. Géron shows you how they work by building one from scratch, and suddenly everything clicks. The tree starts with your entire dataset at the root, like a bouncer looking at a crowd. It asks the best question it can think of, the one that splits the crowd most cleanly. Income above 50K? Boom, the rich folks go left, everyone else goes right. Then it asks another question, and another. Each split creates purer groups until finally, at the leaves, you have your answer. What makes this beautiful is you can actually see the logic. You can trace any prediction from root to leaf and explain exactly why the model made that choice. Try doing that with a neural network. I'll wait. But here's the dark side. Decision. Trees are like that overachiever friend who memorizes the entire textbook instead of understanding concepts. Left unchecked, they'll create a branch for every single training example. If age is 27.5 years, height is 5'8.25, and they wore blue on Tuesday then. That's overfitting, baby. Your model becomes a paranoid detective connecting dots that don't exist. That's why we prune. We limit depth. We demand minimum samples per leaf. We basically tell the tree to chill out and see the forest for the... Wait, that's the next section. Section 7. The wisdom of crowds, ensembles and forests. Here's $1 million insight. One smart person might be wrong, but get a diverse group together, and magic happens. That's ensemble learning. It's why Who Wants to Be a Millionaire had Ask the Audience. The crowd beats the expert almost every time. Géron's about to show you how to build your own crowd of models, and trust me, it's going to change how you think about prediction forever. Enter random forests, the democratic revolution of machine learning. Instead of training one perfect tree, you train hundreds of deliberately imperfect trees. Each one sees a different random sample of your data. Each one randomly ignores some features. They're all slightly drunk on randomness, making different mistakes. But when they vote together, suddenly you have a prediction more stable than your Wi-Fi connection. It's beautifully chaotic. Tree number 47 might be obsessed with income. Tree number 198 is all about location. Tree number 12 had too much coffee and is making weird splits. But average them all together, and the noise cancels out while the signal amplifies. It's like how your random Spotify playlist somehow perfectly captures your mood. Emergent intelligence from controlled chaos. But random forests are just the beginning. Boosting takes this idea and injects it with steroids and a learning algorithm. Instead of training trees independently, boosting trains them sequentially. Each new tree focuses on the mistakes of the previous ones. It's like having a team where each person specifically covers for the other's weaknesses. Tree number 1 makes predictions. Tree number 2 says you messed up on these examples and focuses on those. Tree number 3 corrects number 2's mistakes. By the end, you have a model that's been refined like a samurai sword. And the results? These ensemble methods dominate competitions. They power Netflix recommendations, credit scoring, and medical diagnosis. Because when the stakes are high, you don't want one opinion. You want a consilience of models, each contributing their perspective. But here's the thing. Section 8. Shrink your data, not your brain. Dimensionality reduction. Let me blow your mind real quick. Imagine you're trying to explain your ex to a friend. You could list 1,000 traits. Well, they liked pineapple pizza, wore mismatched socks, cried during Pixar movies, texted in all caps. Or you could just say commitment issues and bad taste. Boom, dimensionality reduction. You just compressed 1,000 features into 2, and honestly, you didn't lose much information. That's exactly what PCA, Principal Component Analysis, does to your data. And when Géron explains it, you'll have that holy crap. Why didn't anyone tell me this before moment? Here's the problem. When your dataset has hundreds or thousands of features, weird things happen. Points that seem close are actually far. Patterns hide in impossible to visualize spaces. Your models get confused, like trying to navigate a city using a 4D map. It's called the curse of dimensionality, and it's why your model with 10,000 features performs worse than the one with 50. More isn't always better. Sometimes it's just more noise. PCA is like a data compression algorithm designed by a minimalist. It looks at your messy, high-dimensional data cloud and asks, what if we rotated our perspective to see the most important stuff? It finds new axes, principal components, that capture the maximum variance. The first component is like the main storyline. The second is the subplot. By component 10, you're in deleted scenes territory. You'll load up the MNIST dataset, those 784-dimensional handwritten digits, and watch PCA compress them down to just 2D. And something magical happens. Suddenly you can see the structure. Similar digits cluster together. 4s hang out with 9s, makes sense, they're cousins. 1s and 7s form their own clique. What was invisible in 784 dimensions becomes obvious in 2. It's like finally cleaning your glasses after months of squinting. But wait, there's more. I sound like an infomercial, but bear with me. Géron introduces TSNE, and this is where things get psychedelic. While PCA is like a wide-angle lens trying to capture everything, TSNE is like a macro lens obsessed with local details. It doesn't care about global structure. It just wants nearby points to stay nearby. The result? Beautiful, organic-looking clusters that reveal hidden patterns in your data. I've seen data scientists literally gasp when they first see their data through TSNE. Customer segments you never knew existed. Fraud patterns hiding in plain sight. It's like those Magic Eye posters from the 90s. Once you see it, you can't unsee it. But here's the catch. There's always a catch. TSNE is an artist, not an engineer. It creates beautiful visualizations, but they're not always reproducible. Run it twice. Get 2 different pictures. It's like asking Van Gogh to paint Starry Night again. You'll get something similar, but never identical. That's why Géron warns use it to explore and understand, not as pre-processing for other models. The real power move? combining dimensionality reduction with everything else you've learned. Reduce dimensions first, then cluster. Compress features, then classify. It's like decluttering your apartment before a party. Suddenly everything works better. But what if your data comes with 0 labels, 0 guidance, 0 anything? What if all you have is raw data and a vague sense that something interesting is hiding inside? That's when things get really fun. Section 9. When there's no labels, unsupervised intelligence. All right, confession time. My first unsupervised learning project was a disaster. I threw k-means at customer data, expecting magical insights. What I got looked like someone sneezed on a scatter plot. Why? Because I was treating unsupervised learning like a magic wand instead of what it really is, detective work, where you don't even know what crime was committed. Géron gets this. That's why he doesn't just teach algorithms. He teaches investigation. Unsupervised learning is like being dropped in a foreign city with no map, no language skills, just your eyes and intuition. You start noticing patterns. These buildings look similar. Those people dress alike. This area feels different. Nobody told you the neighborhoods. You discovered them. K-means clustering is your entry drug. You tell it find K-groups, and it goes to work like an overeager intern, assigning every point to the nearest center. But here's the trick nobody tells you. Choosing K is an art. Too few clusters and you're grouping cats with dogs. Too many and you're splitting identical twins. Géron shows you the elbow method, silhouette scores. But honestly, sometimes you just need to visualize and use human judgment. Because machines are smart, but they don't know that grouping premium customers with about-to-churn customers just because they spend similarly is a terrible business move. Then comes DBSCAN, the rebel of clustering algorithms. While k-means wants everything in neat circles, DBSCAN is like, what if the clusters are weird shapes? What if some points are just loners? It finds dense regions and calls them clusters, labels sparse points as outliers. I've seen it find fraud rings and financial data that k-means completely missed. Because criminals don't organize themselves in convenient spherical patterns. Rude of them, honestly. But the real aha moment comes with anomaly detection. This is where unsupervised learning earns its paycheck. You feed it thousands of normal transactions, and it learns the rhythm, the pattern, the heartbeat of ordinary. Then when something weird happens, bang, it lights up like a Christmas tree. Géron shows you isolation forests, one-class SVMs, and my personal favorite autoencoders for anomaly detection. The idea is delicious in its simplicity. Train a neural network to compress and reconstruct normal data. When something abnormal comes along, the reconstruction is terrible. It's like asking someone to draw a dog when they've only seen cats. The result is interpretable. I once used this to catch manufacturing defects that human inspectors missed for months. The autoencoder was trained on good products. So when a defective one came through, the reconstruction looked like a Picasso painting. Saved the company millions. Did I get a raise? No. But I did get the satisfaction of explaining to executives how we taught a computer to be suspicious. Priceless. The philosophical shift here is huge. In supervised learning, you're the teacher with an answer key. In unsupervised learning, you're the student discovering patterns nobody knew existed. It's humbling, it's exciting, and it leads perfectly to our next evolution. Section 10. Neural nets simulating the brain. Kind of. Okay? Let's address the elephant in the room. Neural networks aren't really like brains. Saying neural networks simulate the brain is like saying a paper airplane simulates a Boeing 747. Sure, they both fly, but one's made of neurons and the other is made of math. Still, when Géron introduces neural networks, something clicks. Not because they're brain-like, but because they're the first models that feel creative. Here's the gateway drug, a simple perceptron. One input layer, one output. It's basically linear regression in a leather jacket trying to look cool. But then you stack them, add layers. Suddenly, you're not just drawing straight lines. You're creating decision boundaries that twist and curve like a roller coaster, designed by M.C. Escher. The magic is in the activation functions. ReLU, rectified linear unit, sounds like a rejected transformer name, but is actually genius in its simplicity. If input is negative, output 0. If positive, let it through. That's it. This tiny nonlinearity is what lets neural networks learn basically anything. It's like adding except to every rule. Suddenly you can model any exception, any edge case, any weird pattern in your data. Géron walks you through building your first neural network for MNIST. And this is where people usually have two reactions. That's it? That's all the code? Why is my laptop now a space heater? Because here's the thing, neural networks are computationally hungry beasts. Every connection is a parameter. Every parameter needs updating. You're not training a model. You're conducting a million-piece orchestra where every musician is learning their part simultaneously. But when it works, chef's kiss. You watch the loss drop, the accuracy climb, and somewhere around epoch 10, your model starts recognizing digits better than your handwriting challenge doctor. But it's not memorizing. It's learning features, edge detectors in early layers, curve detectors in middle layers, full digit templates in final layers. It's building understanding from the ground up, like a child learning to read. The real mind blow comes when Géron shows you the learned features. You can actually visualize what each neuron is looking for. Some are obsessed with loops, others love straight lines. It's like peeking into the model's thoughts and seeing it has preferences, biases, opinions. Not consciousness, but definitely personality. And then you realize this is just the beginning. These fully connected networks are powerful but naive. They treat every pixel equally. They don't understand that nearby pixels are related. They're like reading a book by looking at random letters instead of words, which brings us to the next evolution. Section 11, Why Deep Learning Needs Patience and Power. Real talk, my first deep learning model was so bad, it predicted every image was a cat. Dogs, cats, cars, cats. The number 7, believe it or not, also cats. Turns out I'd accidentally created the world's most optimistic model. It just really wanted everything to be cats. This is what happens when you don't understand training dynamics, and it's why Géron dedicates an entire chapter to the art of not screwing up. Training deep networks is like raising a teenager. You can't just throw information at them and hope for the best. You need patience, strategy, and a shocking amount of computational power. Oh, and just like teenagers, they'll test every boundary you set and find creative ways to disappoint you. First enemy overfitting. Your model becomes that student who memorizes the textbook but can't apply anything in real life. It gets 99% on training data and 60% on test data. Congratulations, you've trained an idiot savant. Géron introduces dropout, randomly turning off neurons during training. It's like making your model study with frequent fire drills. Annoying? Yes. Effective? Absolutely. The model can't rely on any single neuron, so it builds redundancy. It's forced to actually learn instead of memorize. Then there's the vanishing gradient problem, the bane of deep networks. Imagine playing telephone with 50 people. By the time the message reaches the end, it's nonsense. Same with gradients flowing backward through many layers. They shrink to nothing, and your early layers stop learning. They're like, why bother? Nobody listens to us anyway. The solution? Better activation functions. Hello again, ReLU. Better initialization, Xavier He initialization. Fancy names for start with reasonable random weights. And batch normalization, basically keeping your activations from going crazy. It's like therapy for neural networks, keeping them balanced and functional. But here's the part. Nobody talks about watching training curves is addictive. Loss goes down, you feel like a genius. Loss plateaus, you panic. Loss spikes, you question everything. It's an emotional roller coaster. Géron teaches you to read these curves like tea leaves. Smooth descent, good. Oscillating wildly. Learning rate too high, flatlined. You've hit a local minimum, or your model has given up on life. And the tools, TensorBoard becomes your best friend. You're not just training blind, you're watching histograms of weights, tracking gradients, visualizing architectures. It's like having X-ray vision into your model's soul. You start noticing patterns. Oh, layer 3 is barely changing. Layer 7 is going nuts. You become a neural network therapist, diagnosing issues and prescribing fixes. The patience part is real though. Training serious models takes hours, days, sometimes weeks. You'll start a training run before bed and wake up to either Christmas morning, it worked, or a garbage fire, NAN loss, everyone's favorite. You'll become intimately familiar with your GPU's temperature limits. You'll dream about loss curves. But when it works, when you see that smooth convergence, that beautiful generalization, it's better than any video game achievement. You've taught silicon and electricity to see patterns. You're a wizard, Harry. Now, ready to level up? Because raw neural networks are just the beginning. Section 12. Building smart models with TensorFlow. 2. Remember when TensorFlow 1.x made you define computational graphs like you were architecting the matrix? Yeah, those were dark times. TensorFlow 2 is like going from assembly language to Python. Suddenly, you can focus on ideas instead of implementation nightmares. Géron knows this, which is why he teaches TF2 like a native language, not ancient hieroglyphics. First revelation: eager execution. Your code runs when you write it. Revolutionary, I know. No more session.run. Nonsense. You write model.predict. It predicts. You want to debug? Just use print. It's almost like programming. Wild concept. But the real game changer is tf.data. Listen, I've seen data pipelines that would make you cry. Reading CSVs in a for loop, loading entire datasets into RAM. Pre-processing that takes longer than training. It's like cooking a gourmet meal with a campfire and a stick. TF data is your professional kitchen. You build pipelines that stream data like Netflix streams shows. Smooth, buffered, endless. Map transformations for pre-processing, batch for efficiency, prefetch to keep your GPU fed. It's beautiful. Your GPU never starves, your RAM doesn't explode, and training runs like butter on a hot skillet. Géron shows you the pattern load, transform, batch, train. But more importantly, he shows you why each step matters. That shuffle with a buffer? It's preventing your model from learning the order of your data instead of the patterns. That prefetch? It's overlapping data loading with training, basically multitasking for machines. Every piece has a purpose. And custom training loops, this is where you graduate from user to creator. Sure, model.fit is nice, but what if you want to implement a custom loss, gradient clipping, some weird training schedule you read about in a paper at 3 a.m.? With gradient tape, you control everything. Forward pass, loss calculation, backward pass, weight updates, it's all explicit. You're not just driving the car, you're rebuilding the engine while it's running. The best part? It scales. Same code works on your laptop CPU or a massive TPU cluster. TensorFlow handles the distribution, you handle the ideas. It's like having a universal remote for machine learning. Point it at any hardware, press play, and watch your model train. By the time you finish this chapter, TensorFlow isn't just a tool, it's an extension of your thinking. You start seeing problems as data pipelines, solutions as model architectures. And that's exactly where you need to be for what comes next. Section 13. How AI sees images. RNNs demystified. You know that moment when you recognize a friend from across the street, even though they're wearing a hat and you can only see half their face? Your brain doesn't analyze every pixel. It picks up on patterns, the curve of a smile, the way they walk. RNNs do the same thing. Except instead of recognizing your friend doing the walk of shame on Sunday morning, they're identifying tumors, reading license plates, or figuring out if that's a hot dog or not a hot dog. Here's what blew my mind. When I first understood RNNs, they're not looking at images the way we think they are. They're looking for patterns within patterns within patterns. It's like Inception, but for computer vision. Layer 1 is basically asking, are there edges here? It's running these tiny filters across the image. Imagine a magnifying glass sliding over a newspaper, looking for specific letter shapes. One filter loves vertical lines. Another gets excited about horizontal edges. Another is into diagonals, kinky. These aren't programmed. The network learns what to look for. By layer 3 or 4, things get wild. Neurons start responding to corners, curves, textures. There's probably one that's obsessed with circular patterns. Another that fires for anything that looks like fur. They're building a vocabulary of visual concepts, completely unsupervised. And pooling layers, they're the network's way of saying, I don't need to know exactly where that edge is, just that it's in this general area. It's like describing someone as tallish instead of 6 feet 2.5 inches. You lose precision, but gain perspective. And more importantly, you gain the ability to recognize things even when they're slightly shifted, rotated, or scaled. Géron walks you through building a CNN for image classification, and the first time you see it work, it's genuinely magical. You feed it pictures of cats and dogs, because of course you do, and watch it slowly learn to tell them apart. Not by memorizing each image, but by learning that pointy ears, pull vertical pupils, pull general disdain for humanity, oh cat. But here's the kicker. You can actually visualize what the network learned. Using techniques like activation maximization or GradCam, you can see which parts of the image triggered which neurons. It's like asking the model, show me where you're looking, and it highlights the cat's face, ignoring the background. The model learned attention without being taught it. And transfer learning, chef's kiss. Why train from scratch when someone already spent millions training ImageNet? You take a pre-trained model, chop off its head, the final layers, not literally, and attach your own. It's like hiring an experienced employee instead of training a rookie. The model already knows edges, textures, shapes. You just teach it what specific patterns matter for your problem. The applications are everywhere. Medical imaging where CNNs spot cancer better than radiologists. Self-driving cars identifying pedestrians. Instagram knowing that your food photo is, in fact, food, and suggesting the Valencia filter, obviously. Once machines learned to see, everything changed. But static images are just the beginning. What about sequences, time, context? That's where we're headed next. Section 14, Memory and Meaning, RNNs and Attention in NLP. Let me tell you about the time I tried to build a chatbot without understanding RNNs. It responded to, "How are you?" with Pizza Elephant Microscope Tuesday. Technically words, yes. Meaningful sentence? Not so much. That's when I learned that language isn't just about words. It's about memory, context, and the invisible thread that connects thoughts across time. Enter RNNs. The goldfish of neural networks finally evolved to have memory. Unlike traditional networks that treat each input independently, amnesia networks, RNNs maintain a hidden state. They remember. Not perfectly, but enough to understand that bank means something different in Riverbank versus bank account. The basic RNN is elegant. At each time step, it takes two inputs, the current word and its memory of everything before. It updates its hidden state and makes a prediction. It's like reading a book where you actually remember previous chapters instead of treating each word as a fresh surprise. But vanilla RNNs have the memory span of a goldfish at a frat party. After about 10 steps, they forget everything. Enter LSTMs, long short-term memory networks. These bad boys have gates. Forget gates that decide what to throw away. Input gates that decide what's worth remembering. Output gates that decide what to reveal. It's like having a bouncer, a curator, and a spokesman for your memories. Géron demonstrates this with text generation, and watching an LSTM learn to write is surreal. First, it's keyboard mashing ASDFJKL. Then it learns words, Then grammar emerges. The cat is. Finally, it's writing Shakespeare fan fiction. Not good fan fiction, but grammatically correct fan fiction. Progress. But the real revolution? Attention mechanisms. Instead of squashing all previous information into one hidden state, like trying to summarize War and Peace in a tweet, attention lets the model look back at everything. When translating I love you to French, it can focus on love when generating Amy. It's not just remembering, it's selectively remembering. It's the difference between having a photographic memory and knowing which photos matter. And then came transformers. Not the robots, unfortunately, but the architecture that killed RNNs, fortunately. Pure attention, no recurrence. Instead of reading sequentially, transformers see the entire sequence at once and learn relationships between every pair of words. It's like the difference between reading a book page by page versus having the entire book downloaded into your brain, Matrix style. This is what powers GPT, BERT, and every language model that's currently making writers nervous. They don't just understand words, they understand context, nuance, even humor sometimes. They can finish your sentences, answer your questions, and occasionally gaslight you into thinking they're sentient. But here's the thing, all of this, vision, language, understanding, it's still just pattern matching. Incredibly sophisticated pattern matching, but pattern matching nonetheless. The real intelligence isn't in the model, it's in how we use it, combine it, deploy it, which brings us to our final frontier. Section 15. The learning loop, reinforcement, learning. Explained. All right, this is it, the end game. Everything else we've covered, classification, regression, deep learning, it's all been about pattern recognition. But reinforcement learning, This is about decision-making, action, consequences. It's the closest thing we have to teaching machines not just to think, but to choose. Picture this. You wake up in a video game. No tutorial, no manual, just you, a world, and a score that goes up or down based on something. Your job? Figure out the rules by playing. That's reinforcement learning. And once you understand it, you'll see it everywhere. From AlphaGo crushing human champions, to robots learning to walk, to recommendation systems, learning what keeps you doom scrolling. The setup is beautifully simple. You have an agent, that's you, the AI, an environment, the world, actions, what you can do, states, where you are, and rewards, the carrot and stick. The agent takes actions, the environment responds with new states and rewards, and slowly, through trial and error and a shocking amount of computation, the agent learns a policy, a strategy for maximizing long-term reward. Géron starts you with cue learning, and it's like teaching a mouse to navigate a maze. The cue table is basically the mouse's notes. If I'm at position 2.3 and go left, I usually get cheese. If I go right, I hit a wall. Over thousands of attempts, the mouse builds a complete map of state action values. It learns not just what's good now, but what leads to good things later. But tables don't scale. Enter deep Q networks, DQN, the love child of Q learning and neural networks. Instead of a massive table, you have a neural network that approximates Q values. Feed in a state, like pixels from a game screen, get out values for each possible action. It's the same idea, but now it works for complex states like playing Atari instead of mouse in a grid. The real magic is in the details, experience replay, storing past experiences and learning from them randomly. It's like having a dream journal for your AI, preventing it from forgetting important lessons. Target networks, using a separate, slowly updating network for stability. Without this, training is like trying to paint while riding a mechanical bull. And then policy gradients blow your mind in a different way. Instead of learning values, you directly learn the policy. The network outputs probability 70% chance I should go left, 30% right. You sample from this distribution, adding exploration naturally, take the action, observe the reward, and update the network to make good actions more likely. It's elegant, it's intuitive, it's probably how your brain actually works. But here's what nobody tells you about RL. It's hard, like really hard. The feedback is sparse. The exploration-exploitation trade-off is real. You can train for days and get nowhere because your reward function was slightly off. It's like teaching a kid to play piano when you can only tell them their score once a month. Frustrating doesn't begin to cover it. Yet, when it works, chef's kiss. Watching an RL agent go from random flailing to expert performance is genuinely moving. I've seen grown engineers tear up watching their robot finally learn to walk. Because it's not programmed, it learned. Through failure, persistence, and silicon determination. And that's the perfect ending to our journey, isn't it? We started with simple predictions and ended with machines that learn from experience, from pattern recognition to decision-making, from passive observation to active participation. Your move, future builder. All right, we need to talk. You just downloaded 30 years of machine learning evolution directly into your brain. You know how models see, think, remember, and learn. You understand the math, the intuition, and most importantly, the mindset. But here's the thing. Knowing and doing are different universes. Right now, you're at a crossroads. Path 1. You close this video, feel smart for a day, and go back to scrolling. Path 2. You open a Jupyter notebook and build something. Anything. Today. I'm not talking about building the next ChatGPT, I'm talking about starting. Maybe it's a classifier for your photo library, a predictor for your favorite sports team, a bot that texts you when your stocks do something interesting. The project doesn't matter, the building does. Because here's what Aurélien Géron knows that most authors don't. Machine learning isn't learned from books or videos. It's learned from error messages, from models that don't converge. From that moment at 2 a.m. when you finally fix the bug and everything clicks. Every expert you admire started exactly where you are. They just chose path 2. They opened that notebook, imported sklearn, loaded data, and figured it out, one error at a time. So, here's my challenge. Before this week ends, ship something. I don't care if it's a 50% accurate cat classifier or a linear regression that predicts pizza delivery times. Build it, share it, put it on GitHub, post it on Reddit, show your mom, whatever. Just get it out of your head and into the world, because the world needs more builders, not more tutorial watchers, not more certificate collectors. Builders. People who see problems and think I could train a model for that. People who understand that AI isn't magic, it's engineering. And most importantly, people who know that the future isn't something that happens to us. It's something we build, one model at a time, one project at a time. Starting today, starting with you. So, what are you waiting for? Your notebook is calling, your data set is waiting. And somewhere out there, a problem is hoping you'll be the one to solve it. The only question left is, will you? Drop a comment with your project idea. Subscribe if you want more deep dives like this. But most importantly, go build something. The machines are learning. Make sure you are too. Peace out, builders. See you in the future you're about to create.